Okay, so finally it comes to the last talk for this conference for today. And actually I'm Dr. Qin Xiang Chen, and I'm from the Hong Kong Polytechnic University and from the Department of Industrial and Systems Engineering. So today's my talk is about graphene oxide nanofabricated ultrasonic transducers. So to be easier to remember, I call it go nuts. So it's probably it's not easy to forget. So actually, so we know that for today's ultrasonic transducers, we have piezoelectric and CMOS. So these are two main streams for today's research topics. And also we have other materials, new materials, but mostly based on these two kinds of mechanism of operation. And I would like to introduce you another alternative for the ultrasonic transducers for today. And the material we are using is graphene. So we know graphene is single atomic layer material, or we call it 2D material. Let's only have one atom thickness to be around 1 nanometer. So for this kind of material, what can be the good thing for the material? Because we can pack a lot of layers of these 2D materials to make a high density porous structure. And so previously for our project, we try to use this porous structure to store energy. So at first we didn't expect this device can be an ultrasonic transducer. We use the 2D, this porous material to store charges. And probably you know something about the supercapacitor. So you know capacitor can store energy. And the supercapacitor can store energy with high energy density. That probably can be comparable to batteries. So people would like to use this kind of device for future electric cars, etc. And for my previous project, I was working on this kind of device. And for the next project, I need to work on a transducer. So I thought about, because I didn't have enough funding to make a new device. So what should I do? I said, okay, I asked my RA. So probably you can try to use this supercapacitor and give it an AC, right? And if it works, then you don't need to make a new one. Then both of us will be happy. So this is the story of finding the why we found this device can work. And so later I start to study the working mechanism of this device, and mostly it is based on this what we call electric double layer. And the working mechanism of the supercapacitor is also based on this double layer. So this is the fundamental of the supercapacitor. You can see for this interface between the electrode and the electrolyte. So electrode has ions, and these ions can flow to these opposite directions. And at the interface, so if we use it as an energy storage device, we try to pack a very high capacitance, because we can have a very narrow distance between the charges. And this distance can be as small as 0.3 to 0.8 nanometer. That's very, very small. When comparing with CMOS, or when comparing with the dipole distance of the piezoelectric material. So it can store high energy. So what if we try to apply AC to this interface? So actually, it has been found long time ago for electric double layer. When you apply AC, this double layer can vibrate and it can generate sound. However, because this distance is very small, so the sound it generated is also very small. So it comes the important role of the graphene oxide or graphene porous structure, because we can pack hundreds or thousand layers of this 2D material, so we can accumulate this minimum displacement to become something that can generate more power delivery for the ultrasonic application. So I have already mentioned this part. So if you want to understand more, you can key in this EDL compression. Then you can find the fundamental of this. And actually, this has been found like a long time ago. So you know the balance, right? So he also found this mechanism about the electroacoustic phenomenon a long time ago. So as I have mentioned, this is the graphene layers, and we try to make the porous structure of graphene layers. And we use hundreds and thousands of these layers to accumulate this minimum displacement that can generate sound. And it can also, of course, can receive sound to generate the electric signal. And the good thing about this mechanism is because this device is originally designed for energy storage, because it can store a lot of energy. And it also has a high power density, so it can transmit power very quickly. So we don't need a high DC bias or high DC voltage to drive it. We only need something from 1 to 6 volts. That can consider to be very small amount of voltage for the ultrasonic transducers. And of course, we probably cannot go higher, because when we go higher voltage, the electrolyte will also be decomposed. So you know, we know electrolysis, right? It will decompose to something else like gases, etc. So we try to use the compressibility of this porous graphene structure. So when it compresses, it can generate sound. So here comes the beauty of this device. The beauty of this device is you only need a very small investment. You can start to make this device even at home. And it was not invented by me for this kind of process. It has been reported by UCLA group like 3 years ago, but they use it for supercapacitor application. And so for this device, we can use a DVD drive we call Lightscribe to reduce the graphene oxide material to become graphene. So we can pattern it to become arrays, different kind of patterns arrays, 1D, 2D, annular arrays, etc. Just use a very, I would say, very cheap Lightscribe DVD drive. And the Lightscribe DVD drive is used to for the labeling of the CDs. So while you have learned something before, you can use the drive to label the back side of the DVD, and you can have like cover page of the DVD. So this is the type of the drive you need, and it uses the infrared lasers at 700 188 nanometer. And this is the process. You just first drop cast the solution of graphene oxide, and then you wait it to dry, and then you can start to do the laser writing using the Lightscribe DVD. So this is the process, very simple. And after the making of the electrode, you need to do the packaging. The packaging, all you need to do is to use a membrane to separate the two electrodes, and you also need to coat electrolyte to provide the electric double layer to the electrode. So this is the packaging. We have two electrodes, and you have a membrane to prevent these two electrodes get in touch. And then this is the electrolyte we use. That is ionic liquid. So why we use ionic liquid? It's because it can give higher potential window. So we can apply higher voltage, like 4 volts or 6 volts. But of course, we can also use the water-based, like acid or base, that only can give as high as 1 volt of the bias. And this is just a test tube, and this is the packaging of the device. And I would like to show you the testing procedures. So we only apply 4 volts, 20 kilohertz. You use a square wave to trigger the trigger device. And so this is the this is the result. So at first, we try to compare with the ultrasonic transducer made by piezoelectric transducers, and you can see for the receiving for the piezoelectric transducers. So this is the signal of the piezo, and then this is the signal of the gold nuts. So you can see their amplitude is comparable to be 0.15 volts. So the input is only 4 volts, and we can get 0.15 volts. So it can consider to be, I would say, pretty efficient. And this is the another result. So you can see it is also even better than the piezo. So you can see the receiving. And this is result in water. And we use an ultrasonic cleaner to generate the wave, and also to compare with the gold nuts. And you can see the gold nuts even give higher voltage when comparing with the ultrasonic cleaner, which is considered to be a very high energy delivery device, because you use it to clean your jewelry, etc. So this is the bandwidth. Actually, I didn't use the dB. I used I didn't normalize it. But you can compare the bandwidth of the the wave from the ultrasonic cleaner and also the gold nuts, and you can see we have three harmonics. And if you see the you want to the bandwidth is something around 60%, because we use a square wave to trigger it, so it is not that high bandwidth. And here comes conclusions. So what I would like to say is it's something just our findings, and we also want to encourage other friends, colleagues in this conference. You can start to pay attention to the development of this device. Probably you can also try by yourself and to understand, and it's only a minimum investment. The graphene oxide is only probably $20 per gram, and you can play for a long time. So it's a very, and this is the future research. We would like to make some device using the laser light drive. So it comes to the end of my presentation. Thank you. for your attention, and have a safe trip home from Taiwan, because I'm from Taiwan, actually, and I work in Hong Kong.
Thank you. Very